Okay, everyone, let's get started. Great. So welcome all of you to the second colloquium of the quarter. Today I have the pleasure of welcoming Professor Norman Yao from UC Berkeley as our second speaker. Norman is an embodiment of what it means to be an interdisciplinary scientist, in my opinion. He's pushing a new frontier in quantum science that synthesizes and synergizes ideas from AMO, condensed matter, and quantum information physics. He's well known for his deep knowledge of both theory and experiment, but what makes him even more unique is that his group at Berkeley now has successful efforts in both theory and experiment. So a bit about Norm's past. Norm received his PhD from Harvard in 2014, where he worked on a variety of topics ranging from quantum state transfer between qubits in spin chains to realizing new topological phases in cold atom assemblies. Norm then was awarded a prestigious Miller postdoctoral fellow at UC Berkeley. And at Berkeley, he took a real deep dive into quantum dynamics and played a seminal role in the discovery of what are now known as discrete time crystals, which is an exotic out of equilibrium phase of matter that breaks time translation symmetry. And since Norm's work, this has become a major area of interest in the field. Shortly after his Miller Fellowship, Norm was transitioned to becoming an assistant professor at Berkeley. And since that point, he's really further expanded his range of interest and arsenal of skills. He's been working on theoretical aspects of information scrambling and strongly interacting quantum systems. He's been thinking about microwave-based protocols for detecting and controlling magnetic impurities in superconductors. And he's been developing in his lab new instrumentation for imaging local magnetism and various condensed matter systems under high pressure conditions using nitrogen vacancy center based techniques. So for his large body of work, despite his young age, he's already received many awards, including the American Physical Society Debbie Ginn Award for Outstanding Thesis in AMO Physics. He's received a Sloan Fellowship, a Packard Fellowship, and just this year, he was awarded the APS George E. Valley Jr. Prize. So without further ado, let's welcome Norm to the stage.
Great. Can everyone hear and see me at the moment? Good. Thank you so much, Dave, for that tremendously kind introduction. It's really a great pleasure to be able to be here and give you this talk. But at the same time, I'm sad that I'm not in sunny Pasadena with all of you, but rather hanging out in my parents' basement in New Jersey. But nonetheless, excited to be able to tell you a little bit about some of my group's recent work on looking at emergent hydrodynamics and strongly interacting dipolar spin ensembles. Before I even get to sort of a roadmap for the talk, I wanted to start by giving a little bit of a context for how I think about the broad topic of the talk. And there, I think that one of the ways that I like to think about this unifying theme is that we're really trying to understand in some deep sense across AMO, condensed matter, and quantum information, how to make new periodic tables for many-body quantum systems that are very strongly interacting. And the idea there is basically to ask whether or not we can find patterns or to find patterns and guiding principles that help us understand and classify the types of physics that can emerge in these strongly interacting many-body systems. And one place where it turns out there's a very, very successful example of kind of making this type of a periodic table in the strongly interacting many-body context is what I would say is trying to characterize and classify stable phases of matter. And there, I think people at Caltech, Hseih and Alexei have made tremendous contributions to this. But the basic question is very clean. If we're given a microscopic many-body quantum Hamiltonian, one can ask about the nature of the low energy physics of that Hamiltonian, and in particular, what exactly is the nature of the ground state? Natural questions are, does the ground state wave function, for example, is the ground state phase symmetry broken or not? Is it topologically ordered or not? And by asking this question, it turns out one has precisely been able to, I think, in some deep sense, make the analog of kind of elemental periodic tables, but really a periodic table in the many-body context for phases of matter, where there's grouping and patterning according to similar properties and similar paradigms. A question that might be very natural in our minds, given that we start with a microscopic Hamiltonian, is also to ask, what exactly are the dynamics driven by that Hamiltonian, and whether or not one can ask about the same type of characterization and classification questions in the context of quantum dynamics that happen under time evolution of a strongly interacting many-body Hamiltonian. It turns out that up until, I think, kind of relatively recently, people haven't thought about it in this kind of a context of making a periodic table for the quantum dynamics associated with strongly interacting Hamiltonians. And I would argue that there's kind of two reasons for that that can be explained in two basic challenges. The first challenge is that asking this question about quantum dynamics is hard at some level because it's hard to really specify in these types of settings what exactly we mean by system. And what I mean by that is that it's hard to make an isolated many-body quantum system that's also strongly interacting. It turns out that we're very familiar with strongly interacting multi-particle systems, but most of the time, these strong interactions manifest in a multitude of ways. So the degrees of freedom are strongly interacting between each other, but they're also strongly interacting with external degrees of freedom that we typically think of as a reservoir or as the environment. And just to be kind of clear, the delineation that I'm keeping in the back of my mind when I talk about reservoir or environment is I think about the system's degrees of freedom as something that you have some semblance of control over, that you can sort of change the dynamics or modify it in some way. And the environmental degrees of freedom I'm thinking about as things that you have less control over. So making a strongly interacting system that really has strong control, but also interactions among the system's constituent degrees of freedom, but isn't really coupled, but is very well isolated from environment, is kind of the essential starting point for really asking questions and trying to explore quantum dynamics of many-body systems in an experimental setting. And I would say part of the answer to this challenge really comes from the fact that there's been a tremendous genesis in the last decade or so of turning isolated AMO building blocks that afford tremendous quantum control by themselves, individual molecules, individual atoms, individual ions. But there's now really tremendous progress in turning these building blocks into isolated many-body systems that exhibit strong interactions among the constituent particles. I think one of the most promising examples of this is in Manuel Andres's lab right at Caltech, where he's exploring the use of optical tweezer arrays of Rydberg atoms to be able to look at the isolated dynamics of many-body quantum systems. The second challenge, I would say, is maybe even a little bit more fundamental. And that challenge is that it's hard to understand immediately what are the guiding principles for asking how to pattern and classify and understand quantum dynamics of Hamiltonians. In the sort of ground state context, we have a very beautiful paradigm in Landau-Ginzburg symmetry breaking. There's some very well-established statistical mechanical guiding principles for how to think about characterizing phases of matter. On the other hand, when you think about quantum dynamics, it's a little bit weird. You ask dynamical questions and you think immediately about time traces, which means that you can look at different observables in a system. And these different observables in the system you can look at for different amounts of time. You can look at sort of different characterizations of this. And this means that in some sense, there's more choice and less clarity in what questions you should ask about the guiding principles, as opposed to the ground state wave function, which kind of is an object that we can ask questions about in some very natural way. And I think one of the reasons why this challenge has also kind of started to be answered and has allowed one to think about classifying quantum dynamics and really understanding these questions is really the language of quantum information. And thinking about the transport of information dynamics in these systems has led to the ability to take a microscopic Hamiltonian and start to say, do the Hamiltonian dynamics driven by that many-body system, can they be classified and grouped in some way? And indeed, I think we're starting to understand that there are differences, deep differences between the dynamics that are driven by disordered systems, systems that are generically thermalizing, integrable systems, and very recently fast scrambling quantum systems. And it's kind of within this broad landscape of many body dynamics questions that sits the talk that I'll sort of focus on today. I'll try to tell kind of a pretty detailed but specific physics story, and hopefully I'll go slowly enough that everyone kind of follows at each step. But the types of questions that I think are within the purview of this broad set of techniques is asking, for example, if you take a non-equilibrium quantum system, how do the dynamics drive the system to reach equilibrium ultimately? For such a system, do they always reach equilibrium? Can one control the microscopic mechanism and the equilibrium? Are there speed limits, intrinsic speed limits on the nature of quantum dynamics? And it turns out that part of, I think, the richness of this landscape is that there are many, many knobs, both in experiment and theory, to be able to probe these questions. And the same number of knobs leads to an equally exciting number of phenomena that people can observe in these systems, ranging from pre-thermalization to dissipative stabilization of interesting entangled dark states. And it turns out the many knobs and the many phenomena also ultimately means that there are many strategies for attacking these types of questions. It turns out my group has, as Dave mentioned, kind of a theory component where we do quite a bit of numerical work in terms of method development for looking at many body quantum dynamics, as well as quite a bit of analytic work, for example, for proving bounds on the propagation of quantum information in many body systems. But the specific focal point of my talk today will be on a set of experiments that I'm particularly excited about, and I'll hopefully be able to introduce a platform to you for studying these types of questions about many body dynamics. I'd certainly be interested in ideas for what we could explore using this particular platform. With that in mind, let me give an outline for sort of the talk. I'll start with this by introducing kind of the two words in the title. What exactly is this notion of emergent hydrodynamics? It turns out it's an idea that's been around for a long time. I'll give a little bit of a sense of what the lore is, the intuition underlying the lore, and the ingredients in an experimental system that one would want to have to be able to experimentally explore it. Then, within the context of introducing the experimental platform, I'll walk us through the different ingredients that kind of are necessary to be able to explore emergent hydrodynamics within the context of the experimental platform that we're using in my group, which is two strongly interacting but different species of spin defects in diamond. Well, a little aside, a little intermission to talk about expectations from the theory side in terms of what one expects to observe in such a system. And there, I'll emphasize some of the basic assumptions about when one expects to see the physics of diffusion, for example, and why the Hamiltonian that's intrinsic to our system offers both dynamical and static modifications to these expectations. And finally, I sort of, try to give a little bit of a sense of the unconventional diffusion that we're able to explore in the system, as well as hopefully I'll have time to give a little bit of a sense of an outlook on some of the recent things we're working on as well. Good. So what is the lore of emergent hydrodynamics? The lore basically says that given a many-body quantum Hamiltonian, that the late time dynamics of conserved quantities, for example, energy, if one has a time-independent Hamiltonian, or spin, if spin polarization is conserved in the system, is governed by classical equations of motion that look like hydrodynamics. Here, we're mainly thinking about things that look like the diffusion equation as I've written here. And you might say, in some sense, that the fact that the quantum system at late times is governed by classical hydrodynamics is weird and surprising. But in another purview, you might say that it's perhaps not that surprising given our interest these days of thinking about open quantum systems. In particular, you might say that you have, for example, a many-body system, but if there are precisely interactions with an extrinsic environment, these interactions with the environment can lead to the dephasing of intrinsic quantum correlations within the system. And once you dephase all of these correlations, it perhaps is not so surprising that one ultimately sees classical transport at late times. But the question of emergent hydrodynamics, of course, is precisely what I emphasized in the beginning, that really we're asking this question about a closed quantum system. And the idea is that even though you have an isolated many-body system that's not interacting with an environment, the many-body dynamics still are expected within the lore of emergent hydrodynamics to have a classical description at late times. And this is very much related to the idea of thermalization of a many-body isolated system, where the different pieces of the many-body system effectively behave as a bath for the individual components or for local regions of that system. So it turns out, I would say, that this proving that hydrodynamics indeed emerges for a generic many-particle system is one of the most, I think, enduringly hard mathematical physics questions. But even if one doesn't set one's sights quite so high, even taking a specific microscopic quantum Hamiltonian and moving away from full generality, it turns out predicting the hydrodynamical properties, for example, the diffusion coefficient, the viscosity of the sample, are extremely difficult. There exists no generic analytic or numerical tool set to tackle this problem. Our group actually has some recent progress, which was just published, I think, a couple of weeks ago in the paper here, building upon work from Gil Raphael's group using a method called density matrix truncation on the numerical front to explore these types of questions. Good. So kind of with the background definition of what emergent hydrodynamics means, or at least the lore, let me just emphasize again that today's talk is really about looking at emergent hydrodynamics in a many-body spin system that, one, is strongly disordered, and two, has strong long-range interactions in the form of dipole-dipole interactions. But let me give a little bit of intuition for the meaning behind the word emergent. So now that I've kind of explained where the hydrodynamic piece comes from, and really the goal here is to start with something in the back of our mind, which is a microscopic model and some microscopic physical process where we imagine basically coarse graining towards a macroscopic description. So let me start with a simple example that we're all extremely familiar with. We can imagine a classical particle random walking on a lattice. And the idea is that, here we think about there being a polarization per lattice site. And if you coarse grain a little bit by grouping a couple of lattice sites together and a couple more lattice sites together, we can imagine there being sort of a continuous polarization density that has a profile as a function of both time and space. And we know that for this type of a polarization density, that a single classical particle random walking on a lattice ultimately ends up looking like diffusion in late times. This is the classic setting for looking at diffusive behavior for random walks. Of course, in the quantum context, it turns out the physics is very different, and one ultimately sees that for the same problem, a quantum particle random walking or hopping on a lattice, one ultimately gets ballistic behavior. And precisely what people mean when they say that there's emergent diffusion, as opposed to the diffusion in the classical random walking case, is that in this quantum case, once you allow for many, many particles and interactions between the particles, it turns out that the generic expectation at late times is that, again, you see diffusive behavior where conserved quantities are, for example, here governed by the diffusion equation. But now this emerges from the ballistic behavior that initially underlay the single quantum particle walking around. Good. With that lore and that intuition, let me emphasize the kind of natural ingredients that one would hope to have in an experiment to be able to ask questions and to observe this type of physics. It turns out there's long-standing interest in understanding the late-time emergent hydrodynamics or emergent dynamics in general for strongly interacting quantum systems in condensed matter, in AMO systems, as well as in nuclear magnetic resonance systems. The first thing that we've already alluded to is that one needs a conserved quantity. So in our experiments, it turns out that conserved quantity will precisely be spin polarization. Since one wants to watch dynamics, that means that one needs some non-trivial inhomogeneous spin profile. If you have no inhomogeneity in the profile of the spin polarization, there will not be any non-trivial dynamics. So you need an experimental technique to be able to make locally inhomogeneous profiles of the conserved quantity. And that's sort of what I've illustrated over here with this peaked polarization profile. And then you need to be able to have some fiducial probe to be able to measure the quantum dynamics of the system. So to be able to image how exactly that polarization profile changes as a function of time. And ultimately, perhaps one of the most important features is that since we're interested in really distinguishing late time emergent hydrodynamics from early time, for example, local thermalization processes, it's useful and powerful to have a tool set to be able to distinguish between this local behavior and the late time emergent behavior. And of course, then the question is whether or not the late time emergent dynamics can be characterized in some simple classical hydrodynamical equation. And from the experiments, whether or not one can extract out, for example, the diffusion coefficient or the other coefficients within this classical hydrodynamical theory. So with these 4 ingredients in mind, I'll sort of turn to a sort of detailed introduction. I'll hopefully walk through reasonably slowly so everyone is following how we are able to realize these 4 ingredients in the specific experimental platform that we work with in my group. And the experimental platform we work with is, in particular, 2 flavors of coupled spin qubits in diamond, or coupled spin defects in diamond. The first defect that we work with, so diamond itself natively is a tetrahedral lattice of carbons. It has, a relatively large band gap. It's about 5.5 eV. And so defects, for example, sit in the middle of the band gap. And the 2 defects that we're thinking about in my group, one of them is called an NV center. And that corresponds to a situation where a single carbon atom is substituted by a nitrogen impurity. And directly adjacent to that nitrogen impurity is a missing carbon site or a vacancy. So it turns out this NV center is a spin 1 system. So it's really a Q-trit. It's more like a 3-level system. And for the purpose of the talk, I'll actually label the 3 levels as 0, -1, and +1. Turns out the reason why the plus and -1 states are above the 0 state is that there's a single ion anisotropy or a 0 field splitting. That energy scale is typically a few gigahertz in the experimental setup. And most of the time, we'll think about the NV center as kind of the controllable local quantum probe. And this delineation between the NV center and the other defect will be important because it's precisely this delineation that allows us to make inhomogeneous polarization profiles to be able to watch emergent quantum dynamics. The second defect that we work with is a so-called P1 center. And it's basically, not exactly, it's sort of a half the component of the NV center. So it just corresponds to a defect where there's a substitutional nitrogen impurity in place of a carbon atom. And it turns out this is a spin 1/2 defect. And I'll typically in the talk represent that as spin up and spin down. And this system I'll think of as the strongly interacting spin system. Whereas this I'll think about as kind of the local quantum probe that measures the dynamics of the spin system. And just to hammer that point home, the spin system that we work with, we ultimately work with a specific sample where we tune the density of the P1 centers to the NV centers to be such that the P1 density is something on the order of 110 parts per million. This gives you an average spacing between the P1 spins on the order of something like 3 to 3.5 nanometers. And the density of NV centers is about 100 times more dilute. This typically gives you spacing around maybe 30 nanometers or so. Something that's already sort of obvious from this picture, but I should emphasize one more time, is that you can already see that there's intrinsically disorder in the system in the sense that in the diamond lattice, not every single lattice site has a defect. In fact, a very small fraction of the lattice sites have defects. And this means that there's intrinsic positional disorder in the system in the sense that the location of these defects is sort of randomly diluted on the 3-dimensional lattice that, that is the diamond lattice. Good. So with this in mind, let me emphasize that the interactions between these different degrees of freedom, either the NV center and the P1 center, or different P1 centers themselves, is driven by magnetic dipole-dipole interactions. And it turns out one kind of naturally from this magnetic dipole-dipole interaction gets the first ingredient, which is that we need a conservation law to be able to ask questions about polarization dynamics for. And it turns out it's the combination of this magnetic dipole-dipole interaction and the presence of a magnetic field in our system that ultimately causes the effective Hamiltonian dynamics between the NV center and the P1 center to be driven only by energy conserving terms of the dipole-dipole interaction. And because they're only driven by these energy conserving terms, ultimately the terms in the effective Hamiltonian are either of flip-flop form or of Ising form, and this conserves the total number of spin excitations, and this means that we have our conservation law in hand, the first ingredient. In order to understand how exactly we're able to make inhomogeneous spatial profiles of the spin polarization, we first have to introduce a little bit of detail on how one optically controls the physics of the NV center. In particular, as I mentioned, the NV center, you think about, especially from the materials perspective, as a defect that sits in the middle of the band gap in diamond. It's a three-level system, so these are the three ground states that I indicated before. And most of our experiments are at room temperature, which means that from the perspective of the energy splitting that's native to the defect in the solid state environment, which is a couple of gigahertz, basically room temperature is infinite temperature. So in the absence of any initialization, the state of the NV center is basically, an incoherent mixture, 1/3, 1/3 of population in each of these three states in the ground state. It turns out one thing that kind of makes the NV center a particularly well-studied specimen and also kind of finds analogy with atomic physics is that there's kind of a reasonably nice closed optical cycling transition. And what that allows one to do is to optically pump the NV center. And what that means heuristically is that by applying green laser light at 532 nanometers, one can basically cause almost all of the population of the NV center to accumulate in this m sub s equals 0 state instead of being equally distributed. And this initialization also, it turns out, is the same way that one actually gets readout for the quantum system. It turns out that if the NV center is in the state m sub s equals 0, it fluoresces about 30% brighter than if it's in the -1 or +1 states. And this is what allows for both state preparation and readout via optical illumination. At the same time, once one's initialized the system into the m sub s equals 0 state, one can pick one of these two states if one were interested kind of in an effective qubit. One can pick one of the other states as the other piece of the two-level system, and one can perform coherent manipulations, make, for example, superposition states between these two states using microwave driving. And this is exactly what's shown here. Here's the pulse duration of a microwave pulse, and you can see Rabi oscillations, where in the middle of these oscillations, we precisely have a superposition state of 0 and the -1 state. One thing I should really emphasize at this point is that this optical control strategy only works for the NV center. So the same optical illumination of the P1 center does not affect its spin state at all. And that'll be particularly important, the fact that P1 spins are not optically preparable and are dark from the context of the light that affects the NV center is precisely what allows us to ultimately make local inhomogeneous profiles of spin polarization. So let me try to build up that intuition somewhat slowly. In particular, we'll now try to sort of answer this second question: how exactly are you maybe able to make inhomogeneous spin polarization profiles in this experimental system? In order to understand this, we first need to understand the polarization dynamics of the NV center by itself. And the first setting, sort of the first case I'd like to consider, is the situation where we're looking at the polarization dynamics of the NV center, but the NV is off resonant from P1 centers. What I mean by that is that we've applied a magnetic field, and it's for almost all magnetic fields this case. We've applied a magnetic field such that the two levels of the NV center that we'll think about as our effective qubit, in this case 0 and -1, have an energy splitting that's different from the two levels of the P1 center, sort of spin up and spin down, and off resonant in the sense that the energy difference between this mismatch of 0 to -1 and up to down is larger than the typical strength of the magnetic dipole-dipole interaction. And when that's happening, the NV center then is kind of isolated. It doesn't interact at leading order in a resonant way with the P1 centers that surround it. And what you find is that if you prepare the NV center in m sub s equals 0, all of the population here, and you look at the time scale in which the system re-equilibrates to 1/3, 1/3, 1/3, that time scale is extremely long. It's a couple of milliseconds, and typically this depolarization language in sort of the context of AMO is called the T1 relaxation time. So when the two species of spins are off resonant and we look at the NV center, its off resonant T1 time, where its depolarization time scale is relatively long, on the order of a few milliseconds and ultimately driven by phonons. At the same time, in the second case, you can imagine tuning the magnetic field such that the energy difference between the 0 to -1 state of your NV center is precisely on resonance with the down to up transition of the spin 1/2 system that's the P1 center. It turns out this happens in our experimental system at a magnetic field of about 510 Gauss. And when that happens, it turns out one finds that the depolarization dynamics of the NV center are dramatically different. In particular, one finds much more rapid decay of the polarization, almost 3 orders of magnitude more rapid. And so I've called this kind of a T1 in parentheses. So it looks like the depolarization timescale is significantly faster, but the reason why I put this in parentheses is precisely because I want us not to think about this T1 time as an extrinsic depolarization process or as decoherence, but simply as resonant interactions between the NV and the P1 system. So what's happening now is that your NV center and a nearby P1 are exhibiting a flip-flop interaction that are driven by the magnetic dipole-dipole interaction. And when your NV flips because of this interaction, it of course depolarizes, but that loss of polarization is transferring polarization into the system in consideration, the P1 system. In particular, this gives us kind of a very, very nice schematic for how to prepare a polarization profile via a combination of optical pumping and the bare dipole-dipole interactions between the NV and this P1 system. In particular, you imagine that once you've optically pumped, there can be a flip-flop between the NV and the P1 center. But now you can apply another pulse of green light, and that reflips your NV center, it repolarizes it, and then dipole-dipole interactions will cause flip-flops again, and then you can repolarize and dipole-dipole interactions will flip-flop again. And the point is that this process, by doing this process of optical pumping and resonant interactions between the NV and the P1, one naturally gets kind of a soft polarization core of the P1 surrounding any NV center. Let me just emphasize again that the geometry, because of the density mismatch, the NV centers are about 100 times more dilute than the P1 centers, is that you should really think that there's kind of a many-body system of P1 surrounding any NV center. So by continuously optically pumping, you really are taking out the entropy in that way, and using then the dipole-dipole interactions between the NV and the P1 center to basically move that polarization into the P1 system, one creates a soft polarization core surrounding the NV centers. So outside of this core, most of the P1s are at infinite temperature, so equal population of up and down. But within this core, we can think that there's kind of excess polarization precisely that's moved from the NV center to this P1 system. And I emphasize soft because while the NV center is transferring its polarization to the P1 center, the P1 centers are also exhibiting flip-flop dynamics, quantum dynamics between themselves, and this further spreads out the polarization such that one ultimately gets, in principle, a peaky polarization profile precisely as I've drawn over here. And of course, how long you do this procedure for, if you do it for sufficiently long, basically controls how broad or the width of this polarization profile. And typically I'll call the duration of this optical pumping as tau p, sort of the time scale for preparing this type of a soft polarization core. Once we've nominally prepared this polarization core, one can ask a natural question, which is how do we probe it? How in the experiment do we see that there exists this polarization core surrounding the NV center? And the answer to that question is to use the same physics. Precisely, we can look at the depolarization dynamics of the NV center, because as the NV center, as the polarization of the P1 centers is growing around the NV center, it has less neighbors to be able to exhibit flip-flops with. And this means that the lifetime of the polarization, which was very short on resonance, gets longer and longer as the polarization bubble gets larger, precisely because the NV center has less neighbors to be able to lose its polarization to. So the expectation in the experiment is that as you polarize for longer periods of time, you should see that the depolarization timescale, how fast the NV center loses its polarization, gets longer and longer as a function of this polarization duration. And that's precisely what we see in the experiment. For very short polarization periods, you basically see rapid decay, much like what we saw in the bear case where there was no polarization at all. But as you increase the duration of polarization, so you increase the size of this polarization core surrounding the NV center, you find that the time scale of the decay gets longer and longer, and ultimately saturates once you get to polarization timescales that are about 1 millisecond long. And it turns out this basically saturates the timescale at which the NV center would have lost its polarization to the phonons, this sort of off-resonant case, and that's kind of the limit for how long we can polarize within the experimental system. So this kind of harkens at the third ingredient, which is that the NV center also is able to function as a local probe of the P1's ensemble's polarization, and in particular, its own dynamics basically tell you how much of a polarization core, how large the width of the spatial profile is for the P1 system. At the same time, it begs a question. One of the ingredients that I mentioned being particularly important is the ability to distinguish a boundary between local thermalization dynamics, which are kind of short time dynamics, and late time dynamics, which would exhibit emergent hydrodynamics. It turns out you can kind of see from this type of a time trace that there's no clear distinguishing feature between what we would call local dynamics and late time dynamics. And to do this, it turns out one can use a rather simple but kind of clever trick. And in particular, we will make use of this third level of the NV center, which is very far off resonant, and we'll make use of this third level in particular to create an anti-polarized spin configuration. And the idea is that, again, we create some polarization of the P1 centers that surround the central NV center, and then we take the NV's population and we apply a microwave pulse to this highly off-resonant +1 state where we shelve it. And now we apply a microwave pulse that flips all of the P1 spins in the system, but it doesn't touch anything about the NV anymore because all of the population was stored in this +1 state. And then we again apply the same off-resonant microwave pulse to bring the population back to the 0 state. And what that effectively prepares is an anti-polarized configuration where the NV center is pointed opposite the direction of the P1 soft polarization core that surrounds it. And you can imagine this precisely gives us an ability to distinguish between local thermalization. The NV center kind of comes into equilibrium with its local surroundings, and then the long time dynamics where the P1 polarization profile spreads out and ultimately loses its polarization.
Norm, I've got a question from Maria Sparopoulos. I'm going to unmute her if you don't mind and let her.
Absolutely, that sounds fantastic.
Ask.
Hi, can you hear me?
Perfect.
Hello? Yeah.
Hi, Maria.
Norm, can you say a little bit in doing this trick at the lab, how do you maintain the control over all this time?
Yeah, that's a super good question. Yeah. So so I think the question is basically, while we're doing this sort of a shelving trick, is it clear that there aren't dynamics that are happening? And is it also clear that you're sort of not losing polarization? So it turns out that it depends on the time scale of sort of the Rabi frequency, how fast we can apply this pulse, the microwave pulse, compared to the dynamical time scale of the system. So typically in our experiments, the Rabi frequency that we get at is something like 20 megahertz, which means that the pulses are something on the order of maybe like 50 nanoseconds or something like that. And the dipolar dynamics is a very, very good question. Dipolar dynamics, something I didn't emphasize, the interaction strength at kind of 110 parts per million at this 3.5 nanometer spacing is on the order of megahertz scale. So within the time scale of the pulse sequence of applying this shelving trick, very, very little quantum dynamics has happened. And that's the sort of separation of time scales that controls that. Did I answer the question? I'm taking this as tacit consent. Okay, good. So, and yes, let me emphasize, please ask questions. I think all of you know that giving Zoom talks is a different beast. So it would be wonderful to hear questions and please stop me and just call out. Good. So starting from this anti-polarized configuration, it turns out the dynamics indeed look very, very different. In particular, when you look at the polarization dynamics, you find that they, instead of exhibiting a very, very slow decay towards zero, they start exhibiting a very fast decay and going negative. And that's precisely the fact that the envious polarization, which is initially spin up, now very quickly on some fast time scale turns to be spin down. And that's precisely because it's locally equilibrating with the P1 centers that are around it. And then there's a slow decay of this polarization, of the spin down polarization towards zero. And so we can now distinguish sort of this kink by saying that sort of, the local thermalization time for the system is something on the order of 10 microseconds. And only after this time scale is the envy center really a useful kind of fiducial probe of the late time physics associated with the P1's internal dynamics themselves. So let me just take a step back and sort of re-emphasize the style, the general flavor of dynamical experiments that we can envision doing within this particular experimental platform. The idea is that first, we use our envy centers and optical pumping to, for example, create some non-equilibrium polarization profile of the surrounding P1 centers. And then we time evolve the P1 centers under their own intrinsic many-body quantum dynamics. And then ultimately, we probe the resulting polarization using envy centers, distinguishing between local thermalization and late-time emergent hydrodynamics. And from these time traces, we can then ask questions about what exactly is the emergent description of this conserved spin densities dynamics at late times. One thing I should emphasize is that one should, and the reason I put 2 stars here is that I've said in step 2 somewhat easily that we're really time evolving the P1 centers under their own intrinsic dipolar interactions. But this was precisely, the distinguishing feature that I emphasized in terms of emphasizing the word emergent, that we should really have the dynamics of the many-body system driving the diffusion and not some extrinsic dephasing that's driving this. So one can ask a natural question: how in the experimental setting can we be sure that the P1 dynamics are actually dominated by their own intrinsic many-body interactions and not some sort of extrinsic decoherence?
Norm, there's another question, if you don't mind.
Absolutely, please.
The hand just went away. Okay. Oh, Maria has another question. Let her talk.
Fantastic.
Yeah, so thank you for the previous question. Yeah, I didn't have permission to reply to you. Thank you. But can you say something on the step 2 before now? Which calculation the slide, or the next slide rather, here? So how do you do the calculation in order to separate the 2 cases?
Sorry, maybe let me understand the question. So the separate which 2 cases?
So whether it is dominated by the many-body interactions or whether it is
good. Perfect. Yeah. Perfect. Yeah, exactly. Perfect. Yeah. Good. So it turns out that
sorry, maybe it's a little super.
No, it's super clear, and it's a perfect segue to this slide. So it's a great question. The point is that the experimental tool that we have ends up kind of being serendipitously related to the fact that we're working with dipolar interactions. And dipole-dipole interactions are traceless. And it turns out that tracelessness means that there are pulse sequences where you rotate the entire many-body system, and these pulse sequences are able to effectively cancel out, are able to echo out the dipole-dipole interaction. So what I'm showing here is literally the decoherence associated with the P1's system. So the local dephasing time associated with the P1's system under 2 different pulse sequences. One, the XY8 sequence, which does not cancel at leading order or at any order the dipole-dipole interactions between the system. And another, this kind of interaction decoupling sequence, it's really a classic sequence in the context of NMR physics called Wahuha. There's been some recent really nice work from Junhee Choi and company where they've upgraded it and made it much more robust, and that's called the droid pulse sequence. And you can see that the difference is that when you don't decouple the interactions, you see a significantly shorter timescale for the P1's internal coherent dynamics than when you do decouple the dipolar interactions. And this precisely tells us that the actual dynamics of the system are limited at the largest scale by this dipolar interactions between the systems themselves, because you see this coherence extension when you decouple the dipole-dipole interaction. So very good question. So the fact that the P1's coherence time is indeed limited by interactions suggests that in some sense we can think about the system that we're looking at as the sort of emergent regime. So let me now sort of, turn to kind of the broad flavor of these emergent hydrodynamics experiments. And again, it turns out we will use the shelving trick to be able to explicitly distinguish between the non-universal early time dynamics and the late time universal dynamics. So as usual, we start by using the NV center to create a polarization profile of the P1 centers. And then we shelve the NV center to the +1 state so that it's now immune from all of the dynamics of the P1 system. Then we allow the P1 system to equilibrate or diffuse for a certain amount of time, tau d, during which time we expect this polarization profile to spread out. And finally, after this tau d, we bring back the polarization of the NV center, which now looks like an extra very high peak on top of this polarization because the NV's local polarization was not moved at all during the quantum dynamics. So this adds another layer sort of to the profile in the sense that you have kind of a doubly inhomogeneous spin polarization profile. And the very nice thing about this is that it really allows one to distinguish in a single experiment what the local relaxation looks like and what the slow hydrodynamical tail should look like, in the sense that you should expect that this sort of red NV peak very quickly kind of gets eaten into this P1's polarization profile. And then only after that does it sort of now mimic or act as an accurate fiducial probe of the polarization of the P1's dynamics. And indeed, this is exactly what we see in the experiment. So what we find is that depending on, for example, how long we allow the polarization to spread for, you can see a period of rapid decay followed by a slower period of late time dynamics. And it turns out if you wait for a longer period of time, you still have the same form of rapid decay followed by slower late time dynamics. And again, true for all of the timescales that we wait for. And one thing I want to emphasize here is that the late time tail has not been scaled onto itself. The data has not been scaled in any way. The data sort of just falls on top of each other precisely because the NV center, whenever you put it back there, it's always sort of going to be probing whatever the dynamical background is for the P1's polarization tail. And it's precisely the collapse of this tail that helps us identify what really is the late time regime of physics in this kind of a many-body dynamical setting. And we'll sort of go back to analyzing that and trying to understand that in just a little bit. But let me take a little bit of an aside and just give a bit of a theory expectation for what one should maybe expect to see and emphasize some of the distinctions that the Hamiltonian that we have bring compared to conventional diffusion. So I'm sure all of you are super familiar. Conventional wisdom is that, diffusion leads to Gaussians. What does that mean? It means that if you start with a peaky polarization profile, in a very short period of time, you expect that the polarization profile now looks like a Gaussian with a mean square displacement that gets enlarged linearly in time, where the slope of that, the coefficient of that, is precisely 2 times the dimensionality of the system and the diffusion coefficient. An analogous way to characterize diffusion is to look at something called the survival probability. And all that is precisely looking at the height of this polarization profile as a function of time. So if you literally follow this peak as a function of time, this peak will decay and get smaller and smaller as a universal power law. in particular as t to the d over 2. So in 3D, this would predict a universal late time power law of t to the 3/2, where basically the slope of that power law, again, is given by the diffusion coefficient. But it turns out that this form of the diffusion equation makes a couple of fundamental underlying assumptions about the microscopic physics. And those assumptions are most easily seen if we go to Fourier space. So now all I'm looking at is the polarization profile. Previously it was time in real space. Now it's time in K space. And there are a few remarks about the kind of structure factor that governs the diffusion equation. The first is that you see there's no 0th order term, and that comes precisely from the fact that total spin polarization in the system is conserved. There's only K dependence in the system. That actually comes from translation invariance. There's no, for example, derivatives or time dependence, even though in principle P is a function of both time and K. And there's only even terms in the structure factor K squared, K to the 4th, etc. And this comes from locality in the microscopic description. It turns out for our many-body system, the platform strongly violates the last two. I've already emphasized that translational invariance is modified, is violated, and it turns out it's violated on 2 levels. I emphasized when I was introducing the system that there's strong positional disorder in the system. It turns out there's also on-site random fields coming from interactions. You can kind of think about it as like mean field interactions between the spins. And this leads to a dynamical modification of the diffusion equation. You expect it to be dynamical. I'll explain why. And it turns out the fact that we have long-range dipole-dipole interactions that fall off as a power law, in particular as 1 over r cubed, leads to a static modification of this conventional diffusion equation. So let me walk us through kind of each of these effects in turn. The first, this dynamical modification. In our system, translation invariance we know is locally broken. The sort of local environment of each P1, given that we have different positional disorder and different on-site random fields, is going to be different. You can think about it effectively as the landscape of the hopping potential for the particle is changing as a function of space. But what this means is that as a function of this, as a function of different regions or different local environments, these different environments will also naturally have different local diffusivities. So if one allows the same polarization profile to expand in these different settings, one will see that the expansion happens at different timescales precisely because the disorder in the system means that the local dynamics are governed by the local diffusion coefficient and not some global diffusion coefficient. Why does this lead to an intrinsically dynamical modification? Actually, the intuition is super, super nice. If you have a single polarization peak as time goes on and the polarization peak spreads, it averages over a larger and larger region of local environments. And as it averages over a larger and larger region of local environment, it kind of averages over, coarse grains over this effective landscape of different diffusion coefficients. Since this averaging depends on the size of the polarization that's spreading, it has to be an intrinsically dynamical modification. Our conjecture within the context of the experiment is that this can be captured by the leading order dynamical modification to the diffusion equation, which takes the form k squared dt. So again, translation invariance is broken, and thus now we have time dependence in this kind of structure factor. It turns out that this dynamical modification from disorder leads to a pretty striking real space prediction, which is that the functional profile of the spin polarization should be non-Gaussian for extremely long timescales, sort of many thousands of bare tunneling times within the experiment. And it predicts actually that the functional form takes this kind of Yukawa shape, so an exponential divided by a power law. And this is kind of one of the aspects of unconventional diffusion in the sense that here you really see that for very, very long timescales, diffusion does not lead to, for example, Gaussian behavior in the polarization profile. Somewhat interestingly, something that I can't quite sort of fully put my finger on it, it turns out this type of observation that you can get diffusive dynamics whose spatial profile is very far from Gaussian, goes under the moniker of sort of Fickian yet non-Gaussian diffusion. And there it's been seen in many, many different systems, ranging from biological systems, sort of things near the glass transition, colloidal systems, etc. I kind of wonder whether or not all of these can sort of be explained under the same sort of conjectured leading order dynamical modification, this k squared dt term, but I'm not sure about that. Good. In addition to this kind of dynamical modification, there's also static modification. It turns out that it's very natural to think about in systems that have long-range interactions, especially with power law behavior, to compare the power law to kind of the dimensionality of the system. And indeed, that's what you find that the natural modification is, that the conventional diffusion equation is modified to have a long-range contribution that goes as k to the alpha minus d, where alpha is the power law associated with the dynamics, and d is the dimension of the system. It turns out this modification immediately leads to sort of three natural regimes. The first is where this correction dominates over even the first term dk squared, and this means that long-range hops actually dominate over diffusion, and that's the regime of Levy flight behavior. It turns out that you can also work in the regime where the power laws are basically irrelevant, so that this alpha minus d is irrelevant relative to the k to the fourth term, and here diffusion is kind of hardly modified at all. But there's this intermediate power law scale, alpha minus d, between 4 and 2, where long-range interactions lead to a parametrically slower approach to the ultimate diffusive fixed point. And it turns out that's kind of that's the regime where we think our experiments sit in. Good. So with that being said, let me turn back to the data for a second. So we know how to focus on the late time emergent hydrodynamics because we have a collapse of the tail behavior. And if we plot the same tail behavior, but now in a log-log plot, we see pretty clearly approximately a decade of late time behavior that's very consistent with the emergence of diffusion in the system and this t to the 3/2 decay of the survival probability. Turns out that by basically looking at the slope of the survival probability, one can directly extract from the experiments a diffusion coefficient, which gives us kind of a diffusion coefficient on the order of about 0.3 nanometers squared per microsecond. So it's really kind of this controllable local probe of the NV center gives us kind of a very nanoscale window into the emergence of diffusion in this P1 system. But I've emphasized, let me first emphasize that it turns out that there are a number of knobs in the experiment that we can tune. For example, we can tune the effective spacing between the P1 spins by tuning their density. And we can do this by tuning the hyperfine structure using the hyperfine structure of the defect. One can actually also control the disorder in the system by effectively driving the system strong enough to be able to cancel out or echo out the disorder. In both of these situations, one can see modifications to the diffusion coefficient, and one can also see the same sort of late time emergence of hydrodynamical diffusive behavior. But we can ask a natural question, which is, it turns out from the three regimes that I mentioned, if you were following closely, it turns out the power law is 1 over r cubed, the dimension is d equals 3, so it feels like the physics should naturally fall into this ultra long range regime of Levy flights. So why exactly does the system's dynamic actually come out diffusive? It turns out one has to be a little bit more careful, and one has to think deeply about what exactly is the rate at which polarization moves within the many-body system composed of P1s. And here, one has to remember that in addition to there being a flip-flop or a dynamical process where the P1s can move polarization around, it turns out there's also an Ising interaction that naturally ends up being allowed within the energy-conserving terms of the dipolar Hamiltonian. And what this causes is that each NV center basically sees, or each P1 center, excuse me, basically sees an effective random local magnetic field coming from the sum of Ising interactions with all of the other spins in the sample. And this naturally leads to an off-resonance condition between the P1's dynamics, such that they're not really transferring their polarization in a resonant way, which truly would be kind of a 1 over r cubed process, but they're doing so in a way that's governed by Fermi's golden rule. So it's a polarization transfer. And in Fermi's golden rule, the point is that happens really at second order in perturbation theory. And this already gives us insight into why we see this kind of emergent diffusion, precisely because within the polarization dynamics now, the effective power law that governs the long-range interactions is now something that's more consistent with 1 over r to the 6th than 1 over r cubed. And using this kind of nice semi-classical description of the polarization dynamics, it turns out one can very accurately recover that the late time dynamics are described by this type of a gamma, this type of a polarization exchange between the p1 degrees of freedom. In addition to that, one can ask the question, is there any clean signature of this long-range static correction in our system? In particular, you expect that there is precisely, for this 1 over r to the 6th long-range polarization dynamic in 3D, a k cubed correction to the diffusion equation. And it turns out, fitting to a long-range version that has this k cubed term, it's very hard. From the data, it's very, very hard to see this sort of long-range static modification. What's easier to see, and what the semi-classical polarization dynamics give us access to, is what the polarization profile looks like as a function of space as well. And here you can see that in the experiment, the polarization profile, again, looks very, very strongly non-Gaussian. Indeed, it looks very much like an exponential. So here, it's not a log-log plot, it's a semi-log plot. We're only logging on the y-axis. The fact that it's line means it looks very consistent with an exponential. But it turns out that you naturally expect that there is sort of a length scale and a time scale on which the polarization is spread long enough and large enough such that it's coarse graining itself over enough local diffusion coefficients such that you do expect some late time average diffusion coefficient to emerge. And it turns out by combining the values that one gets, one expects this time scale, one predicts that this time scale is something on the order of several hundred microseconds. And you can indeed see from the semi-classical dynamics that at late times, you can see that there's bending over towards this Gaussian behavior, but only at timescales significantly larger than this kind of disorder averaging timescale. I realize I'm running a little bit over, so let me very, very quickly just summarize. I'll sort of skip the outlook for now, but if there are questions, I can go into it. Just a very, very quick summary. I wanted to introduce to you in a little bit of detail to give you a flavor of the kind of many-body hybrid spin system that my group has been exploring, and how one can use it to be able to explore questions like unconventional diffusion, and that in these types of a system, it's very natural to kind of violate the basic operating assumptions that go into many of the emergent hydrodynamic descriptions that people are familiar with, and these can lead to both dynamical and static modifications. Let me just end very, very quickly by acknowledging really a tremendous group of students and postdocs. The work was led by Chong Zhu, Francisco Bingtian, with strong collaborations from Sunwon. On the theory side, it was a tremendously fun collaboration with my good friends Chris Lauman at BU and Joel Moore at Berkeley. Thank you so much for your attention.
Okay, thanks, Norm. So we'll open the floor to questions. I realize we're running a bit late, but we'll take a few. Jason has a question. Let me go ahead and unmute. Yep.
Hi, can you hear me?
Yep.
Hey, great talk, Norm. I wanted to ask whether there's any connection between the system that you discussed and the so-called central spin problem, where a spin qubit interacts with a collection of nuclear spins. It seems to have some common flavors.
Yeah, very much so. So I think that the geometry, the geometry you should think about, at least sort of, in terms of like positional shape, I think precisely should be like a central spin geometry. So in the experiment, it's really sort of, the NV center plays the role of the central spins. The P1s play the role of sort of the ancillary spins around the central spin. And the experiment, it turns out, we kind of average over many central spins. So the experiment isn't focusing sort of the optical measurements on a single central spin, but it's sort of an ensemble of central spins, each with its own sort of, local environment. I guess Yeah, the difference, I mean, depending on sort of which iteration of the central spin model we're thinking about, sometimes people like to think about the central spin problem where the central spin is coupled equal in strength to all of the spins around it. And in that case, so it's really like a circle with a central spin that is the same coupling. That's slightly different than what we have, of course. We have a system where there's, as a function of distance, there's a fall off of the interaction that goes as something like 1 over r cubed. But yeah, the geometry is very similar to central spin problem, which means that, so I think many of the theory questions that people have asked in the context of central spin physics, like many body localization, how does that survive, I think would be interesting and kind of natural questions to ask in this system.
Thank you.
Okay, there's a question from Philip.
Can you hear me?
Yep, perfect.
This is Philip Stamp here, very much involved with the central spin model. I just wanted to point out that when you do have a regular lattice for the spin bath, you actually do get power law decays. And there are a lot of experiments that have shown this back in the 90s, I guess, on dipolar interacting molecular magnet systems, which are just basically large single spins. But I wanted to ask you, I mean, so that I think fits in very much with what you've been saying. But I wanted to ask you, there is another model where you have a particle hopping through a lattice coupled back to a background spin bath. And there one gets a very interesting result, which was finally explained to us by Duncan Haldane, where the motion is initially diffusive, but then you actually get, initially ballistic, but then you get a transition of part of the density matrix of the system to diffusive, and the other part is actually subdiffusive. In other words, showing signs of weak localization. I'm wondering if you ever seen anything like that.
That's interesting. So let me actually, we may need a tiny bit of back and forth just to make sure I understand the question. So the particle, so I'm imagining a sort of a particle that's moving around and coupled to a spin bath. That particle is coupled to the spin bath via its own magnetic moment. It's like a spin hopping around. So it's like moving around, there's orbital motion, but then that spin is also coupled to a spin bath. Is that right? Is that right, Philip? I just want to make sure that I understand the setting correctly.
Description of the result, yes. Sorry, of the model.
Sorry, one more time.
That is the correct description of the model. There is a connection here. Sorry.
Yeah, so I can imagine. So I mean, I think I at least at a high level can understand the physics. Presumably, I wonder if that kind of subdiffusion is again coming from the long rangedness of the interactions. So I think that, I mean, people, Leonid Levitov and people before sort of saw that for the single particle hopping around, once you have, I think about the physics probably as maybe that when it hops around by itself, there's sort of local hopping and that gives you diffusion. But then when you have this long range hopping via the spin interactions, because there's dipole-dipole interactions between the spins of the spin bath, that kind of, if you integrate out the spin bath, that would lead to a long range hopping of the particle. And when that long range hopping, I guess, matches the dimensionality of the system, one indeed precisely can get subdiffusion. It's a super interesting phenomena. Yeah. Actually, that kind of subdiffusion is, I'll be totally honest, that's kind of what we wanted to see at the advent of this project. We were hoping to see the emergence of that kind of subdiffusive behavior that was dependent on both disorder and coupling to the spin bath. But eventually we ended up finding that things were well described by diffusion for very long timescales. Presumably, I mean, I wonder whether or not tuning kind of the strength of the on-site random fields in our system might allow us to get to a different power law regime. I mean, you still expect power laws in the subdiffusive case. It just, it happens that the power law we find is the diffusive power law.
Right. I think we probably should discuss this offline because there's a lot of details here, but the interesting thing is that it happens even if you don't have long-range interactions.
Oh, really? I see. Okay, that I'm not familiar with. That my intuition is wrong then. Okay, yeah, absolutely. It'd be fun.
We were completely confused by it for months. So.
Well, I'm confused. At the moment, I'm confused. So that's.
Okay. Well, I'll get in touch with you.
Fantastic. That'd be great.
Okay.
So Norm, I don't see any other questions in the chat box, the Q&A box, or in the form of raised hands. So once again, thank you for a great talk. And since we're well over time, let me end the colloquium there.
Great. Thanks so much. Thanks so much, everyone.